So what we're doing here today was the homework for today, but I'm not going to collect it, all right? But go ahead and put these in your notes. You're going to need the notes you took, so don't think that doing the notes last night was, oh man, I did work I didn't have to do. Wrong, okay. You should be doing the outline anyway, and it'll help you. So that was a productive learning for you. But let's go through and look at the homework for today. That would be, let's see, the last review question 10, and 3 practice problems in an EPP. So review question number 10. This is the new, what we covered yesterday, the lecture on mole fractions. And remember, the simplistic way of thinking of the mole fraction is percentage. What percentage of the number of moles belong to any given element or any given compound in the mixture? Any given molecules, for example, let's say. So number 10, it says the mole fraction of nitrogen gas in compressed air is 0.78. What's another way of saying that? Say that in a more plain speak, will you? 0.78 is the mole fraction of nitrogen in compressed air. Okay. For every 100 moles of compressed air, or 100 moles of molecules in a container, which is compressed air. What is compressed air? It's a mixture, right? It's air around us compressed. The air around us is a mixture. We talked about this yesterday, or mentioned this yesterday, about nitrogen being the inert gas that's in our air, that's in our atmosphere, that when we breathe, if we didn't have the nitrogen at 78%, we would have too much oxygen. Let's assume that the nitrogen were just gone. We would have the percentage of oxygen in the air would be so high that we would all hyperventilate and die. And if there was more nitrogen in the air, the oxygen would be so diluted that we would all basically be slowly suffocating to death. So, you know, human life on this planet would not exist if the amount of oxygen weren't in a particularly small range, a band that we're familiar with, that we live in. And that percentage is provided by the inert gases, nitrogen in this case, which dilute it out. Our body breathes in the nitrogen, we breathe out the nitrogen. Nitrogen's kind of that filler. Like, you ever take medication or something, you look at it, the active ingredient is 0.1% whatever. Why is the tablet so big? Because they're not about to give you something, say, here, take 1 grain of this. We're not able to separate the 1 grain. So when you take a pill, many times, most of that is nothing. Your body just takes it in, dissolves it, and passes it through. There's no medicine in that at all. But that 1 little grain in there that you really need for the medicine, that's the important part. So that other stuff that isn't effective, it does nothing, it's the inert ingredients. That's what nitrogen does in the air. So what the problem says here is the mole fraction of nitrogen in compressed air is 0.78, which means for every 100 moles of substance that I have in this mixture we know as air, 78 of them are molecules or moles of nitrogen. Nitrogen is 78% of the molecules that we breathe. That's another way to think of it, okay? That's what the 0.78 says. So if you have 1,000 molecules of compressed air, how many will be nitrogen? Remember when we did balanced stoichiometric or reaction equations using stoichiometry? I said 1 atom and 1 atom produce, or excuse me, 1 molecule and 1 molecule produces 1 mole plus 1 mole produces, okay? That the number of moles or the number of molecules is in proportion to the number of moles. If 78% of the moles are moles of nitrogen, 78% of the molecules are molecules of nitrogen. In this case, the X for the nitrogen, this is going to be lovely too, let me see. Yep. just using formulas, if the mole fraction for nitrogen, the X of nitrogen, right, that's our mole fraction for N2, the mole fraction for N2 is 0.78. Okay, 78% of all the molecules are nitrogen. 78% of all the moles of molecules are nitrogens. Okay, so if we have 1,000 molecules, how many of them are nitrogen? Right? Or 0.78, move the decimal 3 places, 1, 2, 3. So we have 780 molecules of nitrogen for every 1,000 molecules of compressed air. All right. That's what, this is just a review question. It's concept. If you understand the concept of what a mole fraction is. And the mole fraction, again, is the percentage of the mixture that is that particular gas. That's the mole. So 78% of the moles, or 78% of the molecules, however you want to say it, are nitrogen in this case. Questions 5, 6 are both related to one another. They build on one another. So let's just look at both of those together. Number 5. As part of an environmental experiment, a mixture of gases is released from a smokestack that's collected in a balloon. Okay? If the mixture is analyzed and found to contain 25 grams of SO2 gas, let's see, so 25.0 grams of SO2, 13.1 grams, 13.1 grams nitrogen monoxide, and 3.5 grams of SO3. What's the mole fraction for each component in the mixture? Okay. Now, shouldn't surprise us looking at a smokestack. What do you see a lot of in the gases? Look at the elements that make it up. Sulfur, right? Smokestacks, gas, sulfur gas is coming out. Okay, so sulfur gas is coming out of the smokestack. So visualize it again. There's a smokestack, smoke coming out of it. You take a balloon, you put it over the end, you collect a volume of gas that came out of the smokestack, you close it off, you take it back, and you're able to find out in the lab that, hey, in this balloon, I have captured 25 grams of SO2, 13.1 grams of NO, and 3.5 grams of SO3. What's the mole fraction for each gas? Okay. Just ask yourself again, what's the basic definition of a mole fraction? Remember, the mole fractions are a unitless number. They have no number. They have no units, I mean. They have a number, but no units. Because we compute that by the number of moles of each gas divided by the number of moles total in the mixture. Right? It's moles divided by moles. What's the unit if moles are divided by moles? Nothing. They cancel each other out. It's just a number. That's why it's a percentage. It's a proportion of. Okay, so the mole fraction is the number of moles of a gas divided by the total number of moles in the sample, in the mixture. So we're talking about moles and moles. Anywhere are we talking about grams? No. So where we are now in chemistry, say, okay, well, I can convert the language of grams into the language of moles, right? I can do that. I can convert grams to moles. What's the Rosetta Stone for doing that? What's the key for converting from grams to moles? Molar masses. And what's the function going to be, the mathematical operation? Divide by molar mass. Right? So for each one of these, we need to be able to come up with the molar mass of a gas, divide the mass collected by the molar mass of each gas, and that should give us the number of moles of each gas. SO2. molar mass of SO2. Sulfur is 32, oxygen is 16. So 32 for SO2 for the two O's, 32 and 32 is 64. So it's going to give me a number. And that's going to be the number of moles. This is grams divided by grams per mole. And it's going to give me moles. 13.1 grams divided by grams per mole. It's going to give me moles. 3.5 grams divided by a certain number of grams per mole is going to give me number of moles. So for nitrogen monoxide, we've got 14 and 16 for 30. And SO3, so it's 16, 32, 48 plus S, 48 plus 32. Was it 80? Okay. This is my math cheat here, because you all know I need it. Go back and check the numbers. We're at number 5. Those are EPPs. Back up just a moment. Yeah, they use 64.1, 30, and 80.1. So their numbers, they come out to be 0.390, 0.437, and 0.440 for the number of moles of each one of those gases present. So if I had said on a test, you have 25 grams of sulfur dioxide, how many moles do you have? Do you feel you could have figured that out? When we're at that place in chemistry, we say, well, I've got the mass, I've got a periodic table, I can figure out how many moles we have. So these numbers here are all from probably, what, 3 or 4 chapters ago, 3 or 4 modules ago. I'm just estimating. So yeah, I can compute these numbers now. Now mole fraction is the new concept we're working on. What is the mole fraction for each one of those gases? So now that I have the number of moles of each gas, to compute the mole fraction is going to be the number of moles of that gas divided by the total number of moles that I have in the mixture. How many moles of these gases do I have? How many moles of material, of matter, are in the mixture? Well, that's going to be the sum of these three, right? I'm going to add all those up. And so we've got 7, 9, 10, 11, 12, 13, 14, 15, 16. Carry the 1, 4, 8, 12. 1.267 moles. Quick add. Yeah, because my answer key is totally wrong. If these numbers are right, it's telling me that I add those 3 numbers up, I get this 0.871.
Yeah, because the 0.440 is supposed to be 0.044.
0.044, that makes sense. Okay. 10, 7, 8, 10, 11, carry the 1, 10, 11, 12, 13, 14, 15, 16, 17, carry the 1, 4, 8. So now they match. 0.871. See? I still use counting up when I do addition. I count it up, and we have 0.871 moles total. If I say how many moles of matter are in that balloon that we just collected on top of the smokestack, 0.871 moles of gas are in that balloon. how much of that gas is sulfur dioxide? Well, 39 moles of it, or 0.39 moles of it is sulfur dioxide. I say, what percentage is that? Oh, well, my mole fraction then, my percentage, that is sulfur dioxide, is equal to the number of moles of sulfur dioxide that I have, 0.390, divided by the total number of moles that I have, 0.871. .448, does it make sense? A little bit less than half, yeah. So my mole fraction is 0.448. Translate that for me. If my mole fraction is 0.448 for sulfur dioxide, what does that tell me about the amount of sulfur dioxide? We have 44.8% of that is sulfur dioxide. By mole count. In other words, if I count up the individual molecules of gas in there, for every 1,000 molecules, 448 of them are going to be SO2 molecules. Nitrogen monoxide. The mole fraction is 0.437 all over 0.871. Again, just a touch less than a half, or a touch more than a half. Yeah, it's just barely more than a half. Yeah, 0.502. Okay, so the number of moles of nitrogen monoxide divided by the total number of moles. So by count, the number of molecules, for every 1,000 molecules, 502 of them are going to be nitrogen monoxide. Another way of saying that, 50.2% of the molecules are nitrogen monoxide. And lastly, mole fraction for sulfur trioxide. Zero 0.044 divided by 0.871. It's about half of a tenth. 0.051. Okay. So, sulfur trioxide. 5.1% of the molecules in there are sulfur trioxide. For every 1,000 molecules, 51 of them are sulfur tri. Okay, so these are the mole fractions for each one of those. The percentage of how many molecules for each gas there are in the sample. The next question builds on that and says, if the total pressure of the gas that you collected is 1.2 atmospheres, what is the partial pressure for each one of these gases? So the balloon, as it filled up, it had 1.2 atmospheres in it. Well, here's the deal. If the balloon didn't have more than 1 atmosphere, what would happen? Would it fill up? Could a balloon fill up if the pressure collected was less than an atmosphere? Because it would be squeezed in by the atmosphere, right? So, but that makes sense then. If the balloon fills, it's stretching against the elastic or the latex. It's filling up. It's got a pressure inside of it then. When you hold it, the balloon has a pressure inside that's greater than outside. That's why it expands. And it has 1.2 atmospheres of pressure inside total. Now the question is, how much of that pressure inside that balloon is due to the sulfur dioxide, the nitrogen monoxide, and the sulfur trioxide? How much of that 1.2? What does Dalton's law of partial pressures tell us? Okay, but that the total pressure is equal to the sum of the partial pressures, right? The first expression of Dalton's law was that the pressure total is equal to the first pressure plus the second pressure plus however many more we have. In this case, the pressure total is due to the pressure due to the sulfur dioxide plus the pressure due to the nitrogen monoxide plus the pressure due to the sulfur trioxide. The total pressure in the balloon is equal to the pressures of each one of the gases in the balloon. Another way of writing what we did yesterday, another expression of Dalton's law of partial pressures, is that the pressure total is equal to the mole fraction for each gas times the total pressure. So in this case, the mole fraction for the SO2 times the total pressure plus the mole fraction times the total pressure plus the mole fraction times the total pressure. Notice, what is the pressure as a result of the sulfur dioxide? The pressure that's due to the sulfur dioxide is equal to the mole fraction of the sulfur dioxide times the total. These three numbers have to equal 1.00. This plus this has to equal 1. Why? Because it contributes to the making of the whole here. A percentage plus a percentage plus a percentage equals the whole. A percentage of the whole. So your mole fractions, they have to add up to be 1.0, whatever, however many places. But they have to equal 1 because they're a fraction of the whole. So the pressure from the SO2, another way to figure that, is the mole fraction of SO2 times the total pressure. Well, if my total pressure is, what do we say it was? 1.2 atmospheres is my pressure total. So my pressure as a result of the sulfur dioxide is equal to the mole pressure, or excuse me, the mole fraction of the SO2 times the total pressure. In this case, SO2, let me put it in the same line. SO2 is 0.448. Total pressure is 1.2. Okay. 44.8% of the pressure is due to the SO2. Why? Because 44.8% of the molecules are SO2. Starting to see the relationships there? It's 44.8% of the molecules, and it contributes 44.8% of the pressure. So then it's the math of the mole fraction times the total pressure. 0.448 times 1.2. .54. I don't have room for the atmospheres here, obviously, but 0.54, what would the units be? If it's 0.448 with no units times 1.2 atmospheres, my answer is in atmospheres because the units carry. The pressure that's due to the nitrogen monoxide is the mole fraction of nitrogen monoxide times the total pressure, which is equal to 0.502 times 1.2. 0.60 atmospheres. And the pressure due to the sulfur trioxide is equal to the mole fraction of the sulfur trioxide times the total pressure, which is going to be 0.051 times 1.2 atmospheres for 0.061 atmospheres of pressure. The 0.061 atmospheres of pressure due to the sulfur trioxide plus the 0.60 atmospheres due to the nitrogen monoxide plus the 0.54 atmospheres due to the sulfur dioxide equals the 1.2 atmospheres total in the balloon. What is the hardest part of this? If you're looking up here, seeing a bunch of math, and it makes you intimidated and scared and say, I can't do that, you're quitting. This is, what part of this is hard? I mean, just think about it for yourself. What part of this is hard? What part of this math is too complicated for a junior in high school to do? Yes, sir.
Remembering the formulas, how to set it up. Because after we did all that, right, then went to the P, SO2 equals X and all that, I was like, wait a minute, what's all this? And then,
Right. So
then, well,
this
I
is
actually started to get it as you went
okay.
to it.
Okay, so it's not the math itself. This is the point. It's not the math itself, right? The math itself is not hard. I hope you agree with me. Multiplication, division, addition, it's not hard. Applying it to the concept, that's what we're pushing against right now, right? The concept. We've got two expressions up here that we're using. Dalton's law of partial pressures and the alternate expression of Dalton's law of partial pressures. So we've worked this out. Let me go ahead and erase this side of the board. I was telling Mrs. Baker that I wished I had here, well, actually I wished I had better than I had in college. Right now we have smart boards, right? And I wish I had a smart board and I can just be doing this stuff. But in my college chemistry class, we had a huge room. I mean, it was probably, I'll try to compare it to a room here in this building. You don't have a classroom that big here. It's probably 3 times as wide and about 4 times, maybe 5 times as deep as this room. Okay, that was my college class for chemistry. Yeah, its closest room was probably the chapel. Okay, and the prof was in the front on a platform raised up in stadium seating, so we're all watching the prof. But he had a platform that went around the 3 sides of the room. And he would start these problems in that corner of the room. Let's say you're looking towards the front. The whiteboard over here, he'd have a whiteboard. He'd start working the whiteboard. When he got to the bottom of the whiteboard, he would slide it left. And there was another whiteboard behind it. When he was done, he would slide it left and work on the next whiteboard below it. And there were 3 or 4 segments. So every time he slid it left, it was just like accordion out, boom, another one, another one, another one. When he got to the end of that 4th whiteboard, he would come over to the front of the class, to the left hand, or to the right hand side, and start working on the 5th whiteboard. We got to the bottom of that, slide it to the left. Got to the bottom of that one, slide it to the left. And so by the time they were done, he would go to the other side there and work back as well, the same process. By the time he was done, you would look to your left and follow all the way around the room, and the solution would be in that corner over there. So you had to flow from one side of the room all the way around, wrapped around to the other side of the room to work your problem. Here I'm struggling with, okay, let me clear this so I can make space to go to the next step. Because let's say that I did 4 problems. Who's to say that what I write on this problem you don't get, but the next problem, it clicks? Wouldn't it be nice to have this still on this? Wait a minute. Oh, I see that now over there. Oh, that makes sense. I can still see with the last problem. It's over here, panel number 2 or panel number 3. So unfortunately, we don't have that option here. I'll do the best I can with trying to organize my thoughts on whiteboard here. So the 2 concepts, we agree the math's not that hard. Dividing a number by a number to get a number. Dalton's law that the total pressure in a space is equal to the pressures of each of the pieces. That another way of saying that is that the mole fraction of 1 times the pressure total plus the mole fraction of the second times the pressure total plus. And to see that pressure 1 is equal to mole fraction 1 total pressure. Me or that? Okay. It's okay. Okay. So what is the pressure contributed by the first gas? If you have the pressure contributed by the first gas, you're probably able to use the initial expression of Dalton's law. If you don't, you're probably working on the second expression that uses a mole fraction. The mole fraction the number of moles of gas 1 these are the four formulas, maybe you think of it this way. This is just pulling out this expression right here. Pressure of the first gas is equal to the mole fraction of the first gas times the total pressure. Same thing with number 2. Tell you what, let's do 7 on the board, and then we'll work EPP. Work the EPP, assuming most of you didn't do it. Work the EPP on your own at your seat, and we'll go over that near the end of class. Okay, let's do that. Number 7. And for those of you that still haven't taken the last module exam, you know, I haven't said when that's going to become a 0, but at some point it's going to become a 0. Number 7. A steel container is filled with 10 atmospheres of nitrogen. So not knowing where we're going yet, let me just write the information down. 10 atmospheres of nitrogen, so N2. Four atmospheres of oxygen. And 1 atmosphere of argon. Actually, they take it out to 2 places. I'll fix that in a minute. What's the total pressure in the vessel and the mole fraction of each gas? Okay. If in a vessel, it's in a container, think of it as a balloon. The balloon is the vessel. If I have 10 atmospheres of nitrogen, 4 atmospheres of oxygen, and 1 atmosphere of argon, what is the total pressure in the vessel, in the balloon? Right. Dalton's law says the pressure total is equal to the sum of the pressures. So there are 15 atmospheres total. Right? There's 15 atmospheres total. That's the first part of the question. What's the total pressure in the vessel? The second part is, what is the mole fraction of each gas? That's what we just did. This total pressure here is equal to the pressure of each of the individual gases summed up. Okay, that's the total pressure. Since we're asked for the mole fraction of each, let's just go ahead and think conceptually. For the equation, what would the equation be? Well, the pressure total is also equal to, another way to write the pressure of N2 is the mole fraction of N2 times the total pressure, plus the mole fraction of O2 times the total pressure, and the mole fraction of argon and the total pressure. Okay? Just formulaically, do you see that those are the same thing? That the pressure of N2 is equal to the mole fraction of N2 times the total pressure. So we know that the total pressure is 15. And the pressure of N2 is equal to the mole fraction of N2 times the total pressure. Do I know the pressure of N2? Okay, let's back up just a second. What am I asked to solve for? The mole fraction of N2. How do I rearrange this equation to solve for the mole fraction of N2? What does it become? Mole fraction N2 equals it's actually pressure N2 divided by pressure total, right? I'm going to divide, think of it this way, divide both sides by pressure total. I'm trying to get mole fraction N2 all by itself. Divide both sides by pressure total. This side becomes over pressure total. This side, pressure totals cancel each other out. So my mole fraction of nitrogen is equal to the pressure from the nitrogen divided by the total pressure. Do I know pressure from nitrogen? I do, don't I? The pressure from nitrogen is 10. The pressure total is 15. Right? That's 2/3. 2/3 is 0.67. 0.6 repeating. But I can only, actually this is, how many places should it have? This is division. I've got 4 over 4. I should take it out to 4 places. So it's 0.6667, right? Did you get it right? Oh, okay, something else. Okay, so the mole fraction of nitrogen is 0.6667. Oh, Chase's number plus 7, yeah, okay. And got it now, okay. The next one, mole fraction of O2, what's that going to be? The pressure of O2 divided by the pressure total. Never mind, never mind. If that's Chase's number, then pressure O2 would be somebody, never mind. Okay, so what's the pressure from O2? Did anybody, okay, did you get it or are you just laughing at me for being dumb? Okay, okay, so then it's our secret. Okay, pressure O2 is 4 over pressure total, right? So 4/15 or 0.267. I looked that one up. Actually, that's wrong. It should be that. 0.267. Okay, sorry, Chase, lost your number. And pressure, mole fraction argon is equal to the pressure argon over the pressure total. Pressure argon is 1 over 15. 1/15. Here's the deal. Now that I know the mole fractions, I could go back and compute, given the pressures and the mole fractions now, I can start making my way into figuring out by percentage how many moles of each gas are there, right? By percentage, for every 1,000 moles, there's 667 moles of N2, 267 moles of O2, and 67 moles of argon. What we're doing here is finding this bridge between pressures and piece counts, okay? Between the moles of the substance and the pressure contributed by that substance through mole fraction. Go ahead and flip back to EPPs. EPP11 is number, or excuse me, EPP chapter 11, number 5. It's a mixture with a mass to compute partial pressures. Why don't you go ahead and start working on that one. I'll join you in about 5 minutes and we'll finish with this. Page 625, number 5. Yes. Mhm. So today is day 9. Okay. So tomorrow is 10. Outline pages 402 through 409. Yep. Don't worry, I think there's labs and stuff in there too. They take up space, so it's not as severe as it sounds. A whole 7 pages. Ah. What's my first step? Just make sure we're working on the right first step. Process-wise, we're converting what to what? Converting grams to moles. So you should be working on converting how many moles of hydrogen, how many moles of CO2, and how many moles of nitrogen. Okay. What? 0.99. 44? Yeah, it's 44, sorry. 16, 32, 12, 44. Yeah, that's 44. Okay, so I have a moment left. Here's the first line. The pressure of hydrogen. Pressure of hydrogen is equal to the mole fraction of hydrogen times the total pressure. Total pressure is 15. What's the mole fraction for hydrogen? Well, if you did this as two steps, you could compute X sub H2, or you could just do it as one single, I did as one single process here. X sub H2 is equal to the moles of H2 divided by the moles total. That's my X number right there. That's my mole fraction of H2 times the total pressure gives me 6.2 atmospheres. When I compute the pressure for each one of these gases, what must the total equal? The total must equal 15. You know that's going to happen when the mole fractions of all three add up to be 1. Because when they add up to be 1, 1 times 15 is 15.